All right, happy Friday, everybody. Today we're going to learn about the instantaneous rate of change because the only thing constant in life is change. And a large portion of math is dedicated to how we can measure change in real world situations. And so today we're going to look at the instantaneous rate of change. So, what we already know is that a constant rate of change is a linear function. So, for example, if John receives $200 from his grandmother for his birthday and places it into a savings account, he continues to save at a rate of $50 per month. That could be defined by the function y equals 50x plus 200 because he started with 200 and continues to save at a constant rate of $50 per month. Next, we learned about the average rate of change, which we learned that if the graph of a function is not a straight line, the average rate of change between any 2 points is the slope of the line containing the 2 points, which we call the secant line. And so what we did here was we just drew a line between 2 points and used our slope formula to find the rate of change. And when we did that, we created an interval that we were measuring, okay? And we call that an interval. So next we're going to look at the instantaneous rate of change. And what the instantaneous rate of change does is it tells me how quickly or at what rate the young man was growing at a single moment in time. And so what we do is we use the secant lines that we learned about before. And as you see here in this diagram, we have line or point P over here, and we have line PD. Then we have line PC, line PB, and line PA. And all of those have slopes that show the average growth rates for successively shorter periods of time or intervals. And what I want you to notice here is that each of these intervals is getting smaller. And not only are those intervals closing and getting smaller, but you'll notice also that all of them are moving closer and closer and closer to point P. So if we desired, we could continue to make points along our curve and continue to make smaller and smaller intervals and get closer and closer and closer to point P. So as it says in the slide, as they approach a single point P, we can measure a single instant in time. And so what happens is, as we continue to draw lines moving closer and closer and closer to point P, these secant lines eventually become what we call a tangent line. So this line right over here going only through point P is going to be called the tangent line. And the slope of the tangent line is the instantaneous rate of change. So as these points all tell me, these other ones, PD, PC, PB, and PA, these other lines all tell me an average rate of change. The slope of this secant line right here is going to tell me how quickly this boy was growing in the moment. In this one moment in time, how quickly was he growing? Okay, so the secant line touches 2 points, the tangent line touches 1 point, and we're analyzing continuous growth over intervals of time at an instant in time. Okay, and we'll see what that means in a moment. So instantaneous rate of change, it's velocity at a moment in time. So if you're driving, you have an average speed, which is an average of how fast you're going at different moments in time. However, when the state trooper uses their radar gun to see how fast you're driving, the state trooper catches you at one moment in time. And that's what we're measuring with instantaneous rate of change, is the velocity at a moment in time. Okay, so let's go to our first example here. And what it says here is the distance f of x in feet traveled by a ball rolling down a ramp is given by the function f of x equals 4x squared, where x is the time in seconds after the ball is released. And then it says here, find the ball's velocity at 1 second using the given intervals, then write the equation for the tangent line, graph the function and tangent line using Desmos. So as you see here, I've given you various intervals. Now, we've already learned before that these intervals are x1 and x2. And what we already know is that in order to find my y values and to use those y values to figure out a rate of change, I would have to insert each of these x values here into my function. Well, what we've done for today is I have created for you a copy, or it's called the instantaneous rate of change, and it's a spreadsheet that's going to do the calculations for you. So all you have to do is enter your intervals, like I'm doing here. And the reason I did this for today is because I want you to focus more on what is happening versus working on calculations. Additionally, these calculations would take you quite a while to do. And I know a lot of you, as much as you love math, don't necessarily want to spend your entire day doing math. So that's why I made this spreadsheet to make things a little bit easier for you. So you'll notice here that as I input everything into x1 and x2, it already plugged those values into the function that I pre-programmed back here. And if you're interested, there's the formula for the function of those particular cells, which is simply the same function here, just rewritten for Excel, or excuse me, Google Sheets. So basically, when I did that, it computed for me a rate of change for each of these intervals. Now notice what's happening to your rates of change. We go from 12 to 11 to 8.4 to 8.04 to 8.00. So what you notice here is that my point is starting to settle down on a value of 8 or 8.0. So that is what my instantaneous rate of change is going to be at 0 seconds. Okay, it's the same way as if I were graphing this. All of those intervals are moving closer and closer and closer to a certain point. And so we see here in this situation that all of these intervals move closer and closer and closer to 8. So when I get 8, 8 is my rate of change, or it's going to be my slope of the tangent line. So what I need to do next is to write the equation of the tangent line, because I cannot graph the tangent line without having an equation for it. So I use my point slope formula, which is y minus y1 equals m times x minus x1. Okay, so I already know my slope is 8. Now, for my y1 and x1, since this is where I finally notice that my point is settling down at 8, I'm going to use x1, which is 1, and y1, which is 4. So that's going to be my x1 and my y1. Okay, so I have 8 times x minus 1 and y minus 4 over here. So now I simply use my point slope formula to find the equation of my tangent line. So I have y minus 4 equals, and then I'm going to distribute the 8. Then add 4 to both sides. So the equation of my tangent line becomes y equals 8x minus 4. Okay, that is the equation of my tangent line. So then I'll come back over here to Desmos, and I will graph both functions. So I have f of x equals, and this was 4x squared. All right, so there is my parabola that represents the velocity of the ball. And then y equals 8x minus 4. And there's my tangent line. And you'll notice right here that here's the point 1,4, and that is precisely the point that I used. And here's where that tangent line touches my parabola. And so at this particular moment in time, my instantaneous rate of change is going to be 8. So that means the ball was changing by 8, as since we're measuring in this particular function, we were measuring the feet that the ball was moving. So at 1 second, it was moving 8 feet per second. All right. So let's go on to number 2, or example number 2, which example number 2 says, if you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate the instantaneous velocity at x equals 0.7 seconds. Use the following function f of x equals 16x squared and intervals to compute the instantaneous velocity. Then write the equation for the tangent line, graph the function and tangent line using Desmos. So again, I will go over here and just, for today, I'm going to use my calculator to enter in these intervals. So x1 is 0.7. And then over here I have point. And the reason x1 is always going to be 0.7 is because that is the point that I'm getting closer to. Okay. And that is the point that we are approaching and the point that we're trying to measure the instantaneous rate of change at. So x1 is always going to be that point. And then all of these other points are points that are getting closer and closer to x1. Okay, so again, as you plug your values in for x1 and x2, or basically place these intervals into the calculator, what you notice here is it gave you the y2. It basically ran the function for you, the 16b squared, or 16x squared. So as you see here, your rate of change starts to settle down. And what point are we settling on? 22.4. So that means that my slope for this particular tangent line is going to be 22.4 at 0.7 seconds. Okay? Because this is the point that we've gotten closer to and we've settled down at. So, same thing as before. I'll come over here and use my slope formula, my point slope formula. So I can get the equation of the line so I can graph this line. So we said 22.4, I believe. Yep, 22.4 is going to be my slope. And then again, for my y1 and my x1, I'm going to use 0.7 and 7.84, since this is the last one. And we see that's where we're approaching is the 22.4. So 0.7 and 7.84. All right, so now we'll just go ahead and distribute the 22.4 to everything in parentheses. And then 0.7 times 22.4 is going to be 15.68. So negative 15.68 plus 7.84 gives me an answer of 8.2. Nope. It's going to give me an answer of 7.84. All right, so there's my equation for my tangent line. So what I do now then is I come over here to Desmos. So this one was 16x squared. And this is going to be y equals 22.4x minus 7.68. And so again, you can see here's your tangent line. I'm going to zoom it out just so we get a better idea. So there's my tangent line to this particular function, which tells me that my instantaneous rate of change at 0.7 seconds is going to be 22.4 feet. So at that moment in time of 0.7 seconds, this coin had moved 22.4 feet. All right, so what I've got for you today is just 3 more slides with problems you can do. I want you to use the rest of this calculator over here to do those, okay? And again, focus on what number you finally approach on your last row here. And what you're going to do is you're going to, as the instructions say, you're going to do just like I showed you, is you are going to, for each of these, find the velocity wherever it's asking you at that moment of time over the various intervals. I give you all of the intervals, and then you're going to use graph the function and the tangent line using Desmos, and then there's an attached Google Doc for you to cut and paste those screenshots into. All right, have a great day, everybody, and come through Google Classroom or Google Meet if you have any questions. Thank you for listening. Have a great weekend.